Hello, everyone. Can everyone hear me? Okay, let me just change back to full screen. Okay, so last chapter, I learned about overloading operator. So I was doing chapter 21 and I did it the parentheses operator and I will finish the rest this stream. So last thing we learned was about overloading the parentheses operator and they said this was the last thing I read. Operator parentheses is commonly overloaded to implement functors or function object, which are classes that operate like functions. The advantage of a functor over a normal function is that functor can store data in member variables. So here's a simple functor, accumulator class. If a private counter class, they have a this overloaded operator. The parentheses operator is overloaded. So every time they call 1, the counter gets added, and then they call 3, counter gets added. This is a separate accumulator object. They're adding 10 and then they're adding 20. So it will print 30. Should I do the quiz? Okay, let's just do the quiz and then I will start the next chapter. Write a class named myString that holds a std string. Okay, I'll just. So, class my string uh, that holds std string. So private std string. I like it when it's on the same line. M underscore string. And then public I should have a constructor for this. So my string std string s. Then I'll have m underscore string s. Is this correct? Hold on. It doesn't seem to be any construct. Actually, yeah, there is a constructor. So I copy this. Wait, how do we do the constructor thing again? The assigning in the constructor. Wait, hold on. So overload this operator to output the string and overload this operator to return the substring that starts at the index of the first parameter as a myString. The length of the substring should be defined by the second parameter. So std ostream, reference to ostream. I'll just remove this for now. Operator so std string, actually my string s out s dot m string, then return out, and then you need to define this parameter. So it outputs a myString, it outputs a myString, and operator this int start int length is there a method inside string which gives the, hold on, m this dot, shouldn't it be like this? The m string dot so let's see, you have m string, want to return a substring, can't we do, hold on, I don't know if this works, return string, hmm, let me see the answer. You can use std string substring. So std string substring, dot substring. Is it like this? And we don't need this. Let's see if this works. Wait, I did not mention out. Std or stream out. Yeah. Why isn't this syntax highlighted? Operator has too many parameters. Wait, isn't this correct? Binary operator has too many parameters. I think maybe I should define it over here. Friend. This is fine. So, and then for the substring, so std string size tag, assert. Why isn't assert? C assert. So assert start is more than or equal to 0. Also assert that length is more than start. Okay, they're also checking whether the length is within range. Assert start plus length is less than or equal to m string dot length. What's the return type of this? Size t. Static cast int and then it needs to be size t. Static cast size underscore t. And then static cast size underscore t. The return type is std string, so I have to change it to my string, right? Okay, I'll make this explicit and then well, this should not work then. Yeah. Now if I do my string all this, now this should work. Yeah, I will go. I need to change something. My laptop is really slow, so I will just go to Task Manager and I will change the priority to above normal. Okay, I'll just go to the next chapter then. Overloading typecasting. In lesson 10.6, you learned that C++ allows you to convert one data type to another. The following example shows an int being converted into a double. C++ already knows how to convert between the built-in data types. However, by default, C++ doesn't know how to convert any of our program-defined classes. In lesson 14.16, we showed how we can use a converting constructor to create a class type object from another type of object. But this only works if the destination type is a class type that can be modified to add such a constructor. What if this is not the case? Take the following class. So sense. Okay. This class is pretty simple. It holds some number of cents as an integer and provides access functions to get and set the number of cents. It also provides a constructor for converting an int into cents. If we can convert an int into cents, then we might also want to provide a way to convert cents back into int. In some cases, this might not be desirable, but it does make sense here. One not great way is to use conversion functions. In this example, we use member function getSent to convert our cents variable back into int, so we can print it using printInt. While this function produces the results we want, it is not truly a conversion, as the compiler would understand that it should use this function for cast or implicit conversion. This also means that if we do a lot of cents to int conversions, our code will be littered with calls to getCents, which is messy. What else can we do? This is where overloading the typecast operators comes into play. Such a typecast can be used explicitly or implicitly by the compiler to perform conversions as needed. Let's show how we can overload a typecast to define a conversion from cents to int. So operator int cast. So overloaded int cast. To do so, we have written a new overloaded operator named operator int. Note that there is a space between the word operator and the type we are casting it to. There are a few things worth noting here. Overloaded typecasting must be non-static members and should be constant, so they can be used with const object. Overloaded typecasts do not have explicit parameters, as there is no way to pass explicit arguments to them. They do still have the hidden this parameter pointing to the implicit object. Overloaded typecasts do not declare a return type. The name of the conversion is used as the return type, and it is the only return type allowed. This prevents redundancy in the declaration. Now in our example, we can call printInt like this. So printInt. The compiler will first note that the function printInt has an int parameter, then it will note that the variable cent is not an int. Finally, it will look to see if we have provided a way to convert cents into an int. Since we have, it will call our operator int function, which returns an int, and the return int will be passed to printInt. Such typecast can only be invoked explicitly via static cast. You can provide overloaded typecast for any data type you wish, including your own program-defined data type. Here's a new class called dollars that provides overloaded cents conversion. So dollars to cents. Oh, and then they are converting to cents will be implicitly cast to int here. Dollars will be implicitly cast to cents here. Wait, hold on. Just like we can make constructors explicit so that they can be used for implicit conversions, we can also make our overloaded typecast explicit for the same reason. Explicit typecast can only be invoked by casting or by form of direct initialization. They are not considered when doing copy initialization. Typecast should generally be marked as explicit. Exceptions can be made in cases where the conversion inexpensively converts to a similar user-defined type. Our dollars operator cents typecast was left non-explicit because there's no reason not to let dollars object be used anywhere a cents is expected. We have cents, we have dollars, we have print cents, a static casting into int. Explicit typecast can only be invoked by casting or a form of direct initialization. They are not considered when doing copy initialization. So we can use explicit cast instead. Oh, so when we do explicit casting will work, but implicit typecasting would not work. Implicit conversion from dollars to cent is okay because it is not marked as explicit. Okay. This would work with both implicit and explicit. So it's working over here. So dollars is converting into cents. When to use converting constructor versus overloaded typecast. Overloaded typecast and converting constructors perform similar functions. In both cases, we start with A and end up with B. The main difference between the two is whether A or B has ownership of how the conversion happens. Since both ways require defining a member function, they can only be used for class types that can be modified. If A is not a class type that can be modified, then you can't use an overloaded typecast. If B is not a class type that can be modified, then you can't use a converting constructor. If neither are class type that can be modified, then you will need to use a non-member conversion function instead. In cases where A and B are both class types that can be modified, we can use either. But since we only need one, which should we prefer? In general, converting constructor should be preferred over overloaded typecast. All other things equal, it is cleaner for a class type to own its own construction rather than rely on another class to create and initialize it. There are a few things where an overloaded typecast should be used instead. When providing a conversion to a fundamental type, most conventionally they use to provide a conversion to Perl for cases where it makes sense to be able to use an object in a conditional statement. When a conversion returns a reference or cost reference, when providing a conversion to a type you can't add members to. When you do not want the type being constructed to be aware of the type being converted from. This can be helpful for avoiding circular dependencies. Okay. For an example of that last bullet, std string has a constructor to create std string from string view. This means string must include string view. If string view had a constructor to create a string view from std string, then string view would need to include string. This would result in circular dependency between headers. Instead, string has an overloaded typecast that handles conversion from string to string view. String view does not know about string at all and thus does not need to include string. In this way, circular dependency is avoided. When a converting constructor and an overloaded typecast are both defined for the same conversion, both are considered during overload resolution. Depending on whether overloaded typecast is constant, the object being converted is constant, and what type of cast or initialization is used. Either function might be chosen. Okay. Well, up in the next chapter, assignment operation. Overloading and the assignment operator. The copy assignment operator is used to copy values from one object to another already existing object. Copy assignment versus copy constructor. The purpose of copy constructor and copy assignment operators are almost equivalent. Both copy one object to another. However, the copy constructor initializes new objects, whereas the assignment operator replaces the constant of existing objects. The difference between copy constructor and copy assignment operator causes a lot of confusion between new programmers, but it's really not that difficult. Summarizing, if a new object has to be created before copying can occur, the copy constructor is used. If a new object does not have to be created before copying can occur, the assignment operator is used. Overloading the copy assignment operator is fairly straightforward with one specific caveat we will get to. The copy assignment operator must be overloaded as a member function. So fraction, we have fraction initialization. We have a copy constructor, fraction. Okay, so this is a default constructor with the numerator and denominator, copy constructor, fraction, a copy of fraction, And okay, no need to check for denominator of 0 since copy must already be a valid fraction. And then overloaded assignment, fraction operator, const fraction. So we have 5/3 fraction f. 5/3 is equal to is assigned to f, calls overloaded assignment. So this calls this, and I'm guessing this calls this. No, it doesn't call the copy constructor. It just replaces the memory content, right? This should all be pretty straightforward by now. Our overloaded operator uh, assign returns this so that we can chain multiple assignments together. Issues due to self-assignment. Here's where things get a little more interesting. C++ allows self-assignment. This will call f1.operator equal f1. And under this simplistic implementation above, all of the member will be assigned to themselves. In this particular example, the self-assignment causes each member to be assigned to itself, which has no overall impact other than wasting time. In most cases, self-assignment doesn't need to do anything at all. However, in cases where assignment operator needs to dynamically align memory, self-assignment can actually be dangerous. Algorithm, IOStream. Okay, the output operator, assignment operator, mdelete, mlength, data null pointer. So where is the self-assignment? First run the program as it is. You will see that the program prints Alex as it should. Now run the following program. MyString Alex 5. So we have data and we have the length. If length mdata new character. So an array of characters. Static cast size t length. std copy in. You'll probably get garbage output. What happened? Consider what happens in overloaded operator assignment over here. So m data delete the data. M string is string.mlength. Then data is null pointer. If mlength, the same thing as before. And then return the existing object so we can change this operator. In this case, mdata is the same as string.mdata. Because it's the same string, both the data are equal. Oh, so when we delete the data, so both the left and right hand gets deleted. The data of the left hand and the right hand get deleted. So when we copy it, when we copy string mdata, there's nothing to copy. Copies mlength elements of string mdata into mdata. The first thing that happens is the function checks to see if the implicit object already has a string. If so, it needs to delete it so we don't end up with a memory leak. In this case, mdata is allocated, so the function deletes mdata. Because string is the same as this, the string that we wanted to copy has been deleted and mdata are dangling. Later on, we allocate new memory to mdata, so when we subsequently copy data from string.mdata into mdata, we are copying garbage because string.mdata was never initialized. Detecting and handling self-assignment. Fortunately, we can detect self-assignment occurs. Here's the updated implementation of the overloaded operator. Okay, so the reference is the same, just return it. Otherwise, everything else is the same. Typically, the self-assignment check is kept for copy constructor because the object being constructed is newly created. The only case where the newly created object can be equal to the object being copied is when you try to initialize a newly defined object with itself. In such a case, a compiler should warn you that C is an uninitialized variable. Second, the self-assignment check may be omitted in classes that are naturally self-assigned, that naturally handle self-assignment. Consider this fraction class assignment operator that has self-assignment guard. If the self-assignment guard did not exist, this function would operate correctly during a self-assignment. Because self-assignment is a rare event, some prominent C++ gurus recommend omitting the self-assignment guard even in classes that would benefit from it. Uh, Copy and swap idiom. A better way to handle self-assignment issues is via what's called a copy and swap assignment. The implicit copy assignment operator. Unlike other operators, the compiler will provide an implicit public copy assignment operator for your class to do if you do not provide a user-defined one. This assignment operator does member-wise assignment. Just like other constructors and operators, you can prevent assignments from being made by making your copy assignment operator private or using the delete keyword. So we have this. No copies through assignment. Copy constructor. So operator, this has been deleted. And the copy constructor is also deleted. Note that if your class has a const memory members, the compiler will define the implicit operator as deleted. This is because const members can't be assigned, so the compiler will assume your class should not be assignable. If a class with const members, if you want a class with const members to be assignable, you will need to explicitly overload this operator and manually assign each non-const member. Okay, next one. Shallow versus deep copying. Because C++ does not know much about your classes, the default copy constructor and default assignment operate memory member-wise uh, member-wise copying can get us into a lot of trouble. Why does it say reconnection successful? Hold on. I should do this above normal. Then I'll do this above normal. And let me check whether my stream is actually working. Okay, it is working, but I don't know why it gave that message. Okay, it is. Uh, when designing classes that can handle dynamically allocated memory, remember why copying can get us into a lot of trouble. This is because shallow copies of a pointer just copy the address of the pointer. It does not allocate any memory or copy the contents being pointed to. Let's take a look at an example of this. So data length and then string length source plus 1. And then we are copying each of the individual data. The above is a simple string class that allocates memory to hold a string that we pass in. Note that we have not defined a copy constructor overloaded assignment operator. Consequently, C++ will provide a default copy constructor and default assignment operator that do shallow copying. The copy constructor will look something like this. String, okay. Note that mdata is just a shallow pointer copy of the source mdata, meaning they both point to the same thing. Now consider the following snippet of code. While this code looks harmful enough, it contains insidious problems that will cause the program to exhibit undefined behavior. Let's break this down by let's break down this example line by line. So my string hello, copy hello, use default copy constructor. Copy is a local variable, so it gets destroyed here. The destructor deletes copy string, which leaves hello with a dangling pointer. Wait, when it deletes copy string, does it delete the m data inside it as well? Uh, this line seems harmless as well, but it's actually the source of our problem. When this line is evaluated, C++ will use default copy constructor. The copy constructor will do a shallow copy initializing copy.mdata to the same address of hello.mdata. As a result, copy.mdata and hello.mdata are now mm, both pointing to the same piece of memory. When copy goes out of scope, the MyString destructor is called on copy. The destructor deletes the dynamically allocated memory that both copy.mdata and hello.mdata are pointing to. Consequently, by deleting copy, we have also affected hello. Variable copy then gets destroyed, but hello.mdata is left pointing to a deleted memory. You can see why this program assignment operator, the overloaded assignment operator, is slightly trickier. Check for self-assignment and now do a deep copy. Note that our assignment operator is very similar to our copy constructor, but there are three major differences. We added self-assignment check. We return this so we can change the assignment operator. We need to explicitly deallocate any value that the string is already holding. This is handled inside deep copy. When the overloaded assignment operator is called, the item being assigned to may already contain a previous value, which we need to make sure we clean up before we assign memory for new values. For non-dynamically allocated variables, we don't have to bother because the new value just overrides the old one. However, for dynamically allocated variables, we need to explicitly deallocate any old memory before we allocate any new memory. If we don't, the code will not crash, but we'll have a memory leak that will eat away our free memory every time we do an assignment. Remember the rule of three: if a class requires a user-defined destructor, copy constructor, or copy assignment operator, then it probably requires all three. This is why if we are user defining any of these functions, it's probably because we are dealing with dynamic memory allocation. We need the copy constructor and copy assignment to handle deep copies and the destructor to reallocate memory. Classes in the standard library that deal with dynamic memory such as std, string, and vector handle all the memory management. And I have overloaded copy constructor and assignment operators that do proper deep copying. So instead of doing your own memory management, you can initialize and assign them like normal fundamental variables. Okay. So this is the last chapter. Overloading operators and function templates. In 11.7, we discuss how compiler will use function templates to instantiate functions which are then compiled. We also noted that these functions may not compile if the code in the function template tries to perform some operation that the actual type doesn't support. In this lesson, we will take a look at few examples in our instantiated functions where our instantiated functions wouldn't compile because our actual class types don't support those operators, and show how we can define those operators so that the instantiated function will then compile. So operators, function calls, and function templates. First, let's create a simple class and define a max function template. So we have max, const. Now let's see what happens when you try to. Okay, so we are doing max, nickel, and dime, assigning it to a picker. C++ will create a template instance for max that looks like this. So cents, cents, and cents. Then it will try to compile this function. See the problem here, C++ has no idea how to evaluate x is less than y when x and y are of type cents. Consequently, this will produce a compile error. To get around this problem, simply operator for any class we wish to use max with. Okay, so they overloaded this operator. And now it says 10 is bigger. Let's do one more example of a function template not working because of missing overloaded operators. The following function template will calculate the average number of objects in an array. So average int array, average double array 4. This produces the value. As you can see, it works great for built-in types. Now let's see what happens when we call this function on our sense class. Sense 5, sense 10, sense 15. Oh, it doesn't know how to do the addition and division. Remember that average returns a sense objects, and we are trying to stream that object to cout using this operator. However, we haven't defined the extraction operator for our sense class yet. Let's do that. So they defined this, but they also have to define the sum, right? And the division. The error is actually being caused by the function template instance created when we call average sense and int. Remember that when we call a templated function, the compiler stencils out a copy of the function where the template type parameter have been replaced with the actual types in the function call. Here is the function template instance for average when t is a sense object. The reason we are getting an error message because of the following line. In this case, sum is a sense objects, but we have not defined this operator for sense objects. We need to define this function in order for average to be able to work. Also, they need to define this operation. So, it's not just plus, it's plus equal to, division equal to. Finally, our code will compile and run. Here is the result, 11 cents. Okay, summary and quiz. In this chapter, we explore related topics related to operator overloading as well as overloaded typecast and topics related to copy constructor. Summary. Assuming point is a class and point is an instance of that class, should you use a normal, friend, or member function overload for the overloaded operator? For the following operators, point plus point, binary point plus is best implemented as a normal or friend function. I want to see what the example of a normal function is. This is a member function. So we have a friend. And then normal function operator plus sense1 and sense2. It's defined like this. Okay, and then this is a friend function. This is a normal function. They are not part of, both of these are not part of the class, right? Then we have member function. How is this defined? I just want to see an example. Sense operator plus okay. So binary plus is best implemented as a normal friend function. Minus point, unary minus point is best implemented as a member function. Then this I'm guessing normal or friend function. And then point is 5. Must be implemented as a member function. Write a class named average that will keep track of the average of all integers passed to it. Use two members. The first one should be of type std in 32t and used to keep track of the sum of all the numbers you have seen so far. The second should keep track of how many numbers you have seen so far. You can divide them to find your average. Write a class named average. So let's see. Write all the functions necessary for a following program to run. So we have average, private, let's see. The first one should be of std in 32t, used to keep track of the sum of all the numbers you have seen so far. Std int 32 underscore t sum, and then int I will call it total, public. So average average. Wait, hold on. No, this is it, right? You shouldn't assign a value to it, right? uh, I don't know if the constructor is correct. So, and then operator, this operator, and it returns std o stream. Std o stream out and average return out. Why is this not syntax highlighted? Should I do const here? Friend so out, let's see, what function should I define? Second should keep track of how many numbers you have seen so far. Can divide them to find the average. I should define a get average function. So should it be a double or float? Let's do double. Get average return sum divided by total. Static cast double. The second should keep up how many numbers you have seen so far. And then get average. Average dot get average. And we need to define the other operator. So plus equal operator. Operator plus equal int num, and then total plus equal 1, and sum is plus equal num. Is this correct? Is it defined like this? Copy average. And the constructor average, like that, like that. Average std int 32t. Actually, average sum is average dot sum, and total is average dot total. It's like this, right? Why is get average over here? Member function can be made const. Yeah. Should this work? Wait, hold on. This over here is going to cause an error. It should return average. Average. And then return this. Shouldn't it be a reference to average maybe? Nope, it should be just average. It says disconnected again. It says disconnected again. Default argument cannot convert is on line 13. Cannot convert from initializer list to average reference. Then line 15, static cast identifier not found. Oh, static cast. And then potential divide by 0. Uh, yeah, that's right, true. If total, then this, otherwise return 0. Let's see the output. 0, 4, 6, 12, 6.5, 6.4, 6.4. Let's see what the issue is. 4, 6, 12, 6.5. Okay. Then plus 6 plus 10 is plus 6 plus 10. Wait. I have a calculator with me. 4 plus 8 plus 24 plus. Where am I getting this error? std cout num total /n. Zero, and then 4 1 12 2 36 26 4. Wait, hold on. I will do another /t. So 4 1, okay, 12 2, 4 plus 8, and then it becomes 12. So the average is 6. And then adding 24, it becomes 36 minus 10, 26, 6.5. Two calls chained together. Then we have 32 and 5, 42 and 6. 4 plus 8 plus 24 plus 6 is 42. Divided by 6 is 7. 42. So why am I getting 6.4? I think maybe I should return it like this. Maybe it's this. I think it's creating a new average object, that's why. Yeah, now it says 7. Instead of int. Int may be 16 bits on some platform, which would mean an average object could only hold a maximum numerator of value 32767. In 32 guarantees a 32-bit integral value. Okay, I will end the stream here. I don't know why it keeps disconnecting again and again. And the next stream, I will continue to the next chapter. Should I do the project? Never mind. I will just continue to the next chapter next stream. Okay, anyways, see you guys next time.